Welcome to The Explainer. Today, we're bridging a really fascinating gap between the academic foundational days of big data and the cutting-edge cloud-native realities of 2026. If you've ever found yourself wondering how the massive data sets powering today's AI and analytics are actually managed behind the scenes, well, you're in exactly the right place. We're going to trace this incredible journey from the original monolithic Hadoop frameworks all the way to the highly unbundled, lightning-fast ecosystems that are running the show today. Real quick, here is our roadmap for today. We'll start with the classic Hadoop foundations, move into MapReduce and streaming patterns, and then explore how the ecosystem unbundled. After that, we'll compare Spark to MapReduce, look at the transition to Kubernetes, and wrap up with cloud-native managed services. We're basically going to look at the original blueprints and then totally tear the house down to see how modern architectures are built.
All right, section 1. Let's begin our journey in the classic era, with the monolithic powerhouse that started it all.
The original Hadoop setup had this just brilliant simplicity to it. It was a tight coupling of core systems, kind of like a perfectly stacked layer cake. At the bottom, you had HDFS providing fault-tolerant storage across a whole cluster of commodity hardware. Right above that sat Yarn, which stands for Yet Another Resource Negotiator, acting basically as the operating system to dynamically allocate computational resources. And then right at the top, you had your compute engines, like MapReduce. This stacked monolithic design was totally revolutionary at the time because it pushed the execution of tasks directly to where the data lived, rather than trying to move massive amounts of data over the network to the compute power. So, in practice, this master worker architecture relied on a really strict hierarchy. You had your master cluster housing the name node and the resource manager, and the name node, it was the absolute boss of the storage. It knew exactly where every single block of data was kept across the vast network of data nodes down in the worker cluster. Meanwhile, those data nodes were just quietly storing the actual data blocks and doing all the heavy lifting. It was highly scalable for its time, but as we'll see in a few minutes, having just one name node trying to keep track of literally everything eventually created a massive bottleneck. Moving on to section 2, let's explore how data was actually processed in this classic ecosystem, because, just storing the data is only half the battle. To process all this information, MapReduce relied on a genius divide-and-conquer parallel processing model. Take a classic word count process, for instance. First, your input data gets split into independent chunks. Then, the map function maps these chunks into key-value pairs, like taking a sentence and tagging every single word with the number 1. Next comes the shuffle and sort phase, which groups all the identical keys together. And finally, the reduced function aggregates those values to give you your final count. It's a highly parallel system, meaning thousands of machines can work on their own little chunk of the puzzle simultaneously. But here's what's actually really cool about this. Hadoop didn't lock you into writing crazy verbose Java code for these tasks. Through a feature called Hadoop Streaming, data engineers could use standard Unix piping to write mappers and reducers in basic scripting languages like Python. By just using standard input and output, a super simple Python script could read a line, strip the white space, split the words, and emit them as key-value pairs. This was a real game changer, because it made debugging incredibly easy. You could literally test your logic right in your local Unix command line before ever pushing it to a massive, expensive Hadoop cluster. All right, section 3, the ecosystem unbundled. Let's fast forward to 2026, where that monolithic house we just built has undergone a massive transformation. We call this shift architectural unbundling. And listen, Hadoop isn't dead. Its foundational principles are very much alive and well, but its original Lego blocks have been pulled apart, upgraded, and containerized for the cloud-native era. Organizations are no longer buying into a single, rigid, all-in-one stack. Instead, they're mixing and matching the absolutely best modular tools available on the market. Now, you might be wondering, why did this unbundling have to happen in the first place? Well, remember that all-important name node boss we talked about? It had a fatal flaw as data footprints started scaling into the hundreds of petabytes. You see, the traditional HDFS architecture stored all the file and block metadata directly within the JVM heap memory of the name node itself. So, when an enterprise hit, say, several hundred million files, the name node would experience severe memory congestion and huge latency spikes. It was effectively suffocating under the weight of its own directory index. To solve this, the storage layer had to be completely unbundled. Enter next-generation solutions like HopsFS and Apache Ozone. Instead of relying on a single, easily overwhelmed in-memory name node, these modern tools decouple the namespace management from the actual block allocation. For example, Apache Ozone uses a specialized ozone manager that persists metadata in RocksDB, pulling it entirely out of those restrictive JVM memory limits. And the results speak for themselves. Benchmarks show these modern storage layers can achieve a 2.6 times throughput increase over traditional HDFS. They easily scale to billions of files without breaking a sweat. Section 4. Spark versus MapReduce. As the storage layer evolved to become faster and more modular, the compute engines obviously had to become smarter and faster to keep up. While MapReduce was an absolute tank, super reliable for big batch jobs, it suffered from heavy disk writing latency. It had to write intermediate data to the physical disk between every single step. That adds a ton of latency. Spark, on the other hand, processes data entirely in memory. It's not just significantly faster, it's also multimodal. That means it can handle real-time streaming, machine learning pipelines, and SQL batch analytics all within one unified engine. This crucial shift from disk to memory is exactly what made Apache Spark the definitive compute engine for modern analytics. So, Section 5 brings us to the Kubernetes transition. If Spark is handling the compute and tools like Ozone are handling the storage, who exactly is managing these resources now that the whole ecosystem is unbundled? This quote hits the nail on the head. The operational shift in data engineering right now is crystal clear. We are actively moving away from Hadoop's traditional yarn scheduler and fully embracing Kubernetes orchestration. Kubernetes brings that much-needed cloud-native agility, allowing engineering teams to containerize their Spark workloads and scale them dynamically right alongside their web apps and microservices. But, and this is a big but, migrating these workloads requires some major trade-offs. Notice how you're trading Yarn's elastic JVM-optimized memory overcommit for Kubernetes' rigid requests and limits. If you don't tune your Spark executors perfectly in Kubernetes, the out-of-memory killer will just terminate your pods without any warning whatsoever. Plus, because compute and storage are now completely separated, Kubernetes has absolutely zero data locality. It has to pull everything over the network, making network bandwidth your brand new bottleneck. Oh, and Yarn's built-in log aggregation? Gone. Engineers now have to scramble to set up external pipelines like FluentD or CloudWatch just to read their container logs before they disappear into the void. Finally, let's head to Section 6 and look at cloud-native managed services. How are the biggest companies actually deploying this unbundled tech today without tearing their hair out managing physical clusters? Managed cloud platforms are the new standard, for sure. Services like Google Cloud Dataproc Serverless let you run wildly complex Spark SQL jobs without provisioning a single node. You literally just submit your SQL, the cloud magically spins up the compute, and then it completely shuts it down when the query finishes. Furthermore, the modern data lakehouse relies almost entirely on open table formats, like Apache Iceberg, Delta Lake, and Hudi. These formats sit right on top of object storage and track data at the individual file level. This gives you amazing features like time travel, schema evolution, and massive scalability, all without being locked into a single vendor's proprietary database. And the business value driving all of this modernization is absolutely staggering. In 2026, we're seeing migrations to managed cloud services massively accelerated by hardware innovations. For example, AWS Graviton4 ARM-based instances are offering up to a 40% performance boost over traditional x86 processors and at a lower cost. Companies are even utilizing agentic AI services like AWS Transform to automatically discover legacy on-premise Hadoop dependencies and literally translate them into cloud-native architectures with something like 99% accuracy. It's all about speed, cost efficiency, and dropping that incredibly heavy maintenance overhead. So I'll leave you with this provocative thought to chew on. Is Hadoop actually dead? We've seen how the monolithic stack was completely broken apart, how MapReduce gave way to Spark, and how Yarn transitioned over to Kubernetes. But the core concepts of distributed storage and parallel processing, the very DNA of Hadoop, are exactly what make today's AI and massive analytics even possible. It definitely doesn't look like the Hadoop of 10 years ago, but its legacy is still quietly running almost every major data pipeline in the world today. Thanks so much for joining me on this explainer, and keep exploring.